Your book and the slides here show a pretty good series of steps for you to use to come up with Lewis dot structures. And kind of like previous sets of rules like assigning oxidation numbers, it's important to do these in the same order that you see listed here. So you want to do step 1 before step 2, before step 3, and so on. And step 1 for drawing any electron dot structure is always going to be to figure out how many valence electrons you have. So remember when we talked about drawing the structures for, say, hydrogen H2 or fluorine F2 or nitrogen or oxygen N2 or O2 respectively, we went over how to do those, and we had to count up not the total number of electrons in each of those atoms, but just the valence electrons, because remember, those are the only ones that are involved in bonding. So what we're going to do is we're going to count up how many valence electrons we have based on all of the atoms in our molecule. And if we have a charge, so if we're dealing with a polyatomic ion instead of a neutral molecule, then we need to add one additional electron for each negative charge, or subtract one electron for each positive charge if it's a cation. The next step is going to be to connect our atoms. Now, for any atom to be part of the molecule or polyatomic ion that we're going to be drawing, it's going to need to be connected to at least one other atom with at least a single bond. So we're going to draw lines to represent bonds between atoms, and initially we're just going to put down single bonds, so single lines. And there are some guidelines here to help you figure out how to arrange these. So hydrogen and halogens usually form only one bond. Hydrogen can only form one bond, it can't form two or more. Likewise for fluorine, one of the halogens, that will only ever form one bond. The other halogens have a tendency to form one bond, but it's not absolute for chlorine, bromine, or iodine. And elements in the second row usually form certain numbers of bonds based on their position in the periodic table. And to a certain extent, if you look at the elements directly beneath any of the elements in the second row, they'll have usually the same number of bonds and lone pairs as the elements above them, although with row 3 and below, there are some exceptions to that. It's more absolute for the elements in the second row. So if we look at our second row nonmetals, including semimetals, so we're ignoring lithium and beryllium, starting with boron, you can see the number of valence electrons for the elements in each of these columns in row 2 go 3 for boron, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine, and 8 for neon. Now, if we start from boron, which has 3 valence electrons, the number of valence electrons is equal to the typical number of bonds that forms. So for instance, if we look at a compound between hydrogen and any of these elements, what you'll find is that for boron, the basic molecule for that is going to be BH3, which contains 3 boron-hydrogen single bonds. If we look at carbon, which has 4 valence electrons, it'll form, generally speaking, 4 bonds. So the prototypical example of carbon and hydrogen would be methane, CH4, which has 4 carbon-hydrogen single bonds. Now, starting with nitrogen, as the number of valence electrons increases, the number of bonds is actually going to go down. So for instance, nitrogen has 5 valence electrons, but it doesn't form 5 bonds typically, it typically forms 3. So nitrogen and hydrogen together give you ammonia, NH3, which has 3 nitrogen-hydrogen single bonds. With oxygen and hydrogen, of course, we get water. That has 2 OH single bonds. So again, you can see this pattern that occurs after carbon, where if we increase the number of valence electrons by 1 from the 5 in nitrogen to the 6 in oxygen, we're actually going to decrease the number of bonds. And finally, if we move on to fluorine, which has 7, we're going to decrease the number of bonds again by 1. So HF, for instance, hydrofluoric acid or hydrogen fluoride, I guess, if it's not dissolved in water, it just has 1 hydrogen and fluorine single bond. And of course, as we know, neon, like pretty much any noble gas, doesn't form compounds at all, so it's not going to bond to anything else. You can't form a bond between neon and hydrogen. So that recaps sort of what the general trends are there. Keep in mind, for instance, if you go down into row 3, a lot of those same trends will apply. So for instance, silicon, the element directly beneath carbon, will typically also form 4 bonds, since it also has 4 valence electrons. All the elements in the same columns are going to have the same number of valence electrons. Now, elements in the third row and lower often do behave that way, and when they're part of a molecule, elements in the third row and below are almost always going to be at the center of the molecule. And it's also possible for elements in the row 3 and below to form more bonds than is predicted either by the previous chart or by the octet rule. So what I mean by this, if we look at the highlighted portion of the periodic table, you can see we've got those same groups of elements, boron through fluorine, but instead of being in row 2, we're now in row 3 and below. The elements highlighted in blue there do tend, in many cases, to behave the same way as their row 2 equivalents in the same group, because they have the same number of valence electrons. However, they are larger atoms, and so there will be plenty of examples where we'll see they can have actually more bonds than you'd predict based on the octet rule. So that's step 2. I know it's kind of vague. You kind of need to work through lots of examples to get a good feel for how exactly this should work. Now, for step 3, which of course you'll apply after step 2, where you've basically assigned the central atom and attached the other atoms to that central atom, what we're going to do next is assign electrons to the terminal atoms. So the atoms on the outside, we're going to use lone pairs of electrons from the total number of valence electrons we have available to complete their octets. So of course, any element pretty much is going to want to have 8 valence electrons around it. Now, with hydrogen, remember, its electrons are in a 1s orbital, so to complete that orbital you just need 2. So hydrogen's not going to have 8 electrons around it, it's going to have 2, because it wants to be like helium, which is its nearest noble gas equivalent. But all the other noble gases have 8 valence electrons, and so pretty much any other element will want to have a full octet. If we have any electrons left after step 3, we're going to assign those to the central atom, because at that point we really don't have anywhere else to place them. And then step 5 is going to be to essentially analyze that central atom, determine if it has a full octet, and use one or more lone pairs of electrons from neighboring atoms to form a multiple bond, either a double or a triple bond, if we have a situation where we don't have a full octet around our central atom. So what we're going to get into next is to look at several examples step by step. I'll show you the ones on the slides, kind of walk you through those. I'll also post a video going over a couple examples from the book where, just like we did when we were meeting in class, you can look up those problems, you can try to do them on your own, and then after you've made an attempt to do that, I will have a video for you to look through the explanation for that. So let's start with a simple example. However, this one's going to be a little bit less simple than the first Lewis-Dot structures we looked at, where we just had 2 atoms. So if we want to draw an electron-dot structure for water, H2O, we're now moving on to a situation where we have 3 atoms. So remember, step 1, and this is a step that applies to every single molecule you'll ever draw, is to count the number of valence electrons we have. So water, H2O, each molecule has 2 hydrogen atoms and 1 oxygen atom. Each of those hydrogens is going to bring 1 valence electron to the party, and the 1 oxygen will bring 6. So if we multiply our 1 valence electron from each hydrogen by 2, the number of hydrogens, That gives us 2, plus the 6 from the oxygen gives you 8 valence electrons. Now, so that's the number of valence electrons we're going to have to draw from to put our molecule together. Step 2 is to use some single bonds to connect the atoms together. Now, remember, part of this is going to be to figure out which atom belongs in the center of the molecule, essentially. Now, hydrogen is almost always never going to be at the center of a molecule for the simple reason that it can only have basically a single bond and no other lone pairs or attachments to other atoms. So you can't have a hydrogen with, say, 2 atoms attached to it. Therefore, hydrogens are basically always going to be terminal atoms, in other words, not at the center. So since we can't use hydrogen for a central atom, we only have one other choice, which is oxygen. So in step 2, we're going to put that oxygen in the center of our molecule, and by that I mean that's going to be the atom to which our hydrogens, the other atoms, are attached. So you can see we have single bonds between oxygen and hydrogen, and for any molecule at step 2, you only assign single bonds, and we'll come back to multiple bonds at step 5 if it applies. Now, step 3 in this process, after you've attached those hydrogens to your oxygen, is to assign electrons to your terminal atoms, which in our case would be hydrogen, to complete their octets. And remember, hydrogen will only have 2 electrons around it instead of 8, so we're not going to be able to assign any more electrons to our hydrogen for the simple reason that our hydrogen has 2 electrons available to it with the single bond. So remember, each bond contains a bonding pair of electrons, so each of those hydrogens has access to 2 electrons via the bonding pairs between it and the oxygen. So there's no electrons to place down in step 3. And if we account for how many electrons we've placed so far, we started with 8. Each of those single bonds has a pair of electrons, or 2 electrons, and since there's 2 of those bonds, in step 2 we've used up 4 of our 8 electrons, so we have 4 more to place down. Since we couldn't place any of those in step 3, step 4 says we need to take our remaining electrons, of which there are 4, we're going to put those on our central atom. So since we have 4 electrons, the best way to do that is going to be with 2 lone pairs of electrons. And remember, those can be represented with 2 dots for a pair of electrons. So our oxygen will have 2 lone pairs for a total of 4 non-bonding electrons. And if we count up all the electrons after step 4, we've used up exactly 8 of them, so we don't have any more electrons to place. And then step 5 would be to check the octet of our central atom to see if we need to add any more electrons to it via forming double or triple bonds, for instance. And our oxygen has 8 electrons around it already, which is the ideal amount according to the octet rule, so we're not going to form any double or triple bonds. And in the case of water, the hydrogens don't have any lone pairs for us to do that anyway. So we're done after step 4. That structure you see in step 4 there is the final correct structure for water. So let's move on from water to another example. This one will be carbon tetrachloride, CCl4. So for carbon tetrachloride, of course, for any molecule, in step 1 we need to count up how many valence electrons we have. Carbon has 4, chlorine, being a halogen, has 7. All halogens have 7 valence electrons. Since there are 4 chlorines, we need to multiply that 7 by 4, and then add the 4 from our 1 carbon, we get 32 valence electrons to place down in this structure. So the next step is to connect our atoms. Now, there are several guidelines for assigning the central atom. One good guideline is whenever you see carbon, it's pretty much always going to be at the center of a molecule. Carbon has a tendency to form bonds to multiple different atoms, and therefore is pretty much always a good candidate for the central atom. But if you're not sure, one good principle to apply is look at the elements in your molecules. In our case, that would be carbon and chlorine. If in doubt, go with the less electronegative element for the atom in the center. So if you look up the electronegativity values, which is on a previous slide, carbon is less electronegative than chlorine. So we could use those guidelines as well to tell us to put carbon in the center of the molecule and put chlorines as the terminal or outside atoms. So in step 2, we'll put carbon in the middle, meaning we're going to attach each of our 4 chlorines to that at least one time. So we put down single bonds there. We have to have at least one bond between each of our atoms and another atom, otherwise they wouldn't be bonded to the molecule in any way and they wouldn't be part of it. So in step 2, we've used up 4 single bonds. Remember, each of those bonds is a pair of electrons, so that's 8 electrons used up out of the 32. So 32 minus 8 means that after step 2, we have 24 electrons left. Step 3 tells you to look at our outside atoms, so our 4 chlorines, and to use the remaining valence electrons to complete their octets, assuming we have enough electrons to do that anyway. So I just said we have 24 valence electrons left after step 2. So in step 3, it turns out that each of those chlorines, after step 2, only has access to 2 electrons via the single bond it has to the carbon. So each one would like to have 6 more electrons to end up with a total of 8. Remember the octet rule, oct means 8. So if we put 3 lone pairs on each of our chlorines, that'll give us 6 more electrons, plus the 2 in the bond gives us 8. And so we have 8 electrons around each of our chlorines if we were to add 3 lone pairs to each of them. So 3 lone pairs is 6 electrons. If we do that 4 times, 6 times 4 is 24. So that uses up all 24 remaining electrons after step 2. So once we put in all of those lone pairs you see in step 3, we're going to have all the electrons placed in the molecule. So step 4, which only applies if we have electrons remaining after step 3, doesn't really apply. So nothing to do in step 4. Step 5 is to check our central atom, make sure it has an octet of electrons available to it. And if you look at that carbon, it's got 4 single bonds around it. And remember, again, each of those bonds is 2 electrons because it's a bonding pair. 4 times 2 is 8 electrons. So our carbon is perfectly happy with the number of electrons it has. And so there's nothing to do in either step 4 or step 5. So the structure we have there after step 3 is the correct final structure for carbon tetrachloride.